All right, so get this. Predicting the weather without relying on, those traditional weather models, those intricate ones.
Yeah, it's a pretty wild idea, isn't it?
Right.
This new system, they're calling it GraphDOP, and it learns directly from observations of the Earth system. So basically, like bypassing all that other stuff and going straight to the source.
So is it like throwing out the old cookbook for weather prediction and writing a new one just straight from observation?
That's a really good way to put it.
Okay.
You see traditional numerical weather prediction or, NWP,
Mhm.
it relies super heavily on what's called reanalysis data.
Reanalysis data. Okay, so for someone like me, break that down.
Sure. So think of it like this. It's basically like a blend of past forecasts and actual observations.
Okay.
And they use that to kind of create a starting point for, new
Oh,
predictions.
so it's like they're using the past to try and see the future?
Exactly. It's really computationally expensive, though.
I bet.
Requires complex algorithms and, you have to be constantly fine-tuning it.
Yeah, that sounds like a lot.
It is, and it's been successful, but all that complexity has pushed researchers to look for different ways of doing things,
Yeah.
especially using, machine learning and things like that.
Right.
And that's where this graph DOP comes in.
Okay, so instead of reanalysis data,
Yeah,
it's going straight to like the raw data.
exactly.
Wow, and what kind of information are we talking about here?
So things like satellite brightness, temperatures,
Okay.
conventional measurements, so like temperature, wind speed, all that stuff.
So it's learning from the raw ingredients.
Exactly.
Wow. That seems like such a different way of thinking about weather prediction than we're used to.
It really is. And here's where it gets even more interesting.
Okay.
It operates solely in observation space.
Observation space.
Yeah.
That sounds kind of abstract.
It is. It's a little out there, but basically it means it's not relying on any pre-existing model outputs or, those like gridded weather maps you're used to seeing.
Yeah.
So imagine trying to understand a city just by observing people and traffic, but without using a map. That's kind of what this is doing.
So it's learning by just watching what's happening.
Yeah.
Wow. But how does it make sense of all that information?
So it uses what's called a graph neural network.
Okay.
GNN, they call it.
Right, GNN got it.
Think of it like a giant web that's constantly changing.
Okay.
Each node in that web is an observation, and the connections between them are based on, how close they are in space and time.
Oh, so the closer the observations are, the stronger the connection.
Exactly, and these connections are constantly shifting, so it's like a dynamic representation of what the Earth system is doing.
Okay, so it's like a living map almost.
Yeah, like a living, breathing thing.
That's incredible.
But training a model on this raw data comes with challenges.
Oh, I bet like what?
Well, observational data is messy.
In what way?
It can be scattered, there's gaps in it, there's errors, it's not perfect.
It's not a perfect system.
No, it's not. And they also have to deal with the fact that sometimes what they're observing is only indirectly related to the weather that they're actually interested in.
Oh, so it's like they're trying to see the forest, but they're looking at like individual leaves.
Right.
Okay, so how do they handle all that?
So to tackle that, their training data set, it prioritizes observations that capture like the large-scale atmospheric structure.
Okay.
And they focus on what's called level 1 data.
Level 1, what is that?
So that's the raw calibrated readings right from the instruments.
Okay.
And they very specifically chose to exclude certain derived products.
Oh, so they don't want to taint it with anything.
Right. Like, for example, atmospheric motion vectors.
Right.
They left those out because those could introduce bias from pre-existing models.
Right, so it's like they're starting from scratch.
We're starting with a clean slate, exactly.
But how do they prevent it from being overwhelmed by just the sheer amount of information that's coming in?
Right. So this current model, they trained it on 18 years of data. Yeah. And it includes a wide variety of instruments and data types.
Wow, okay, so 18 years of weather data, that's a lot to process.
It is. It's a ton.
What kind of results are we seeing from all this?
Well, the early results are really promising.
Oh, yeah.
It's shown surprising accuracy in predicting satellite brightness temperatures,
Okay,
especially the ones that are sensitive to surface conditions.
so it can see what's happening on the ground.
Kinda, yeah.
What about, like, tracking weather systems over time? Can it do that?
It's been really successful with that, too.
Oh, wow.
Like, for example, it accurately tracked a frontal cloud feature moving across Europe over several days.
So it's not just predicting, like, isolated events. It's actually seeing the movement.
Right. It's capturing the dynamics.
That's impressive. Are there any, like, specific events where its predictions were particularly interesting?
Yeah, there are a couple that really stand out.
Okay.
One was a rapid sea ice freezing event in the Arctic. And GraphDOP accurately predicted it just based on the initial atmospheric state and its understanding of how the Earth system works.
So it's like it knows how the pieces fit together.
It's understanding the connections.
That's amazing. What other examples were there?
Another interesting one was its performance in predicting Hurricane Ian.
Oh, Hurricane Ian, that was devastating.
It was.
Yeah.
And while it did a remarkable job forecasting, the hurricane's path
Okay.
and even the formation of its eye, it did underestimate the storm's speed.
Okay, so there are still some kinks to work out.
Yeah, it highlights some limitations that are still there.
But even with those limitations, it seems like the potential is huge.
Oh, absolutely.
So in a nutshell, what are some of the key strengths and weaknesses you've seen so far?
One of the most impressive strengths is its ability to make accurate predictions up to 5 days out.
5 days?
Yeah, and in some cases, it's actually outperforming those traditional methods we talked about.
Wow, that's a pretty significant time frame for weather forecasting.
It is, but on the other hand, as we saw with Hurricane Ian, it can struggle with accurately predicting the storm speed.
Right.
And it also has trouble with some other variables like surface temperature.
Why is that?
It's likely a combination of things.
No.
There just aren't as many relevant observations available at the surface compared to higher up in the atmosphere.
Right.
And the measurements themselves are more complex. There are more factors at play.
So it does better when there's more data and the measurements are more straightforward?
Exactly.
Makes sense.
That.
But I remember you mentioning some ideas for how to improve these models.
Yeah.
What are some of the most promising areas for development?
Well, one key area is refining that weighting system we talked about.
Oh, right.
By tweaking how they prioritize those observations. They can enhance its accuracy and its ability to capture those key atmospheric features.
So it's like fine-tuning the settings to get the most out of the data.
Right. It's all about optimization.
Very cool.
Yeah.
And what else?
Another avenue is incorporating a wider range of data sources. Currently it's mostly satellite data and conventional measurements.
Right.
But there's so much other data out there. Think about citizen science initiatives, privately owned weather networks.
Oh, yeah, that's true. We're collecting weather data all the time now from our phones to our smart homes.
Right. Imagine what we could do if we could tap into all that.
It would be incredible.
As these models get more sophisticated, they'll be able to integrate all these diverse and complex data streams.
It's like we're giving them a whole new way of seeing the world.
Yeah, like a sixth sense almost.
So with all this talk about potential, what does it mean for the future of weather forecasting in general?
That's the big question, and that's what we're going to explore next.
All right, I'm excited to hear more.
There's so many possibilities from these hybrid forecasting systems to, the implications for our understanding of climate. It's really vast.
Okay, well, let's dive into it.
Let's do it. You mentioned earlier GraphDOP was trained on, data from all these different instruments.
Yeah.
Can you tell us a little bit more about those?
You're right. They used a variety of satellite instruments, but maybe instead of listing every single acronym, can you just give us the big picture, like what kinds of instruments are we talking about and what do they actually measure?
Yeah, that's a good point. It can get really acronym heavy.
Yeah.
Basically, they focused on instruments that can capture the large-scale temperature and moisture structure of the atmosphere.
Okay.
So that includes 3 main types: microwave sounders, microwave imagers, and infrared sounders.
Okay, so it's like having 3 different sets of eyes looking at the atmosphere.
Yeah, exactly.
Can you break down what each one does?
Sure. So let's start with microwave sounders.
Okay.
These instruments, they measure microwave radiation that's emitted by the Earth's atmosphere.
Okay.
And by analyzing this radiation, we can figure out things like temperature and humidity at different altitudes.
So it's like a vertical thermometer.
That's a really good analogy.
Okay, cool.
Then we have microwave imagers.
Okay.
These give us more of a broader view of atmospheric conditions.
Measuring things like precipitation, cloud cover, sea ice.
So more like weather cameras almost.
Exactly, giving you that snapshot.
Yeah.
And then finally, we have infrared sounders.
Okay.
They're similar to microwave sounders, but they measure infrared radiation, which is particularly sensitive to temperature variations.
So by combining data from all 3, they're getting a much richer picture.
Exactly. It's a multidimensional view of the atmosphere.
And it's not just limited to satellite data, right?
Right. They also included conventional measurements from things like weather stations on the ground, weather balloons, radiosondes, even aircraft observations.
Wow, so it's pulling data from everywhere.
Yeah, they're really trying to get a complete picture.
But with all that information coming in, how did they prioritize what the model should focus on?
So they have this weighting system. where they
Oh,
prioritize certain observations during the training process.
okay.
So, for example, observations that are considered more reliable or ones that capture key features of the atmosphere.
Like
Yeah.
measurements related to tropospheric temperature, those were given higher weights.
So it's like quality over quantity.
Right, making sure the model's focusing on the good stuff.
But what about like errors or inconsistencies in the data? How did they deal with that?
That's a good question. They had a number of quality control procedures
Okay.
to try and filter out, obviously bad data points.
Yeah.
One method they used was kind of an ERA5 departure check.
Wait, ERA5, isn't that a reanalysis data set?
It is.
I thought the whole point was to move away from those.
You're right to point that out.
Yeah.
But it's important to note that ERA5 was only used for quality control.
Okay.
They were very careful to make sure that it didn't actually influence the model itself.
Got it.
It was more like double-checking the observations against a reliable reference point.
So it's like a safety net.
Exactly.
Oh.
They didn't want it to become a crutch for the model,
Yeah.
because ultimately the goal is to have a truly observation-driven system,
Yeah.
completely independent.
Okay, but speaking of, those achievements of GraphDOP,
Yes.
you mentioned it showed some impressive skill in predicting specific events.
Yes.
Can you tell us a little bit more about those examples?
Absolutely. One of the most compelling ones was this accurate prediction of a rapid sea ice freezing event in the Arctic.
Wow.
This was particularly tricky to predict
Yeah, I bet.
because it involved such a complex interplay of atmospheric conditions and sea ice dynamics.
So what made GraphDOP's prediction stand out in this case?
It was able to look at the initial state of the atmosphere, things like temperature, wind patterns, cloud cover,
Okay.
and infer that the conditions were right for this rapid ice formation.
So it wasn't just recognizing a pattern, it was understanding the process.
Exactly. It was seeing those connections.
That's impressive.
And that ability to infer information from seemingly unrelated data points, that's one of the most exciting things about AI DOP models.
It's like they're seeing things we can't.
In a way,
What other examples were there?
another notable one was its performance in forecasting Hurricane Ian.
Right.
While it did underestimate the hurricane's speed,
Yeah.
it accurately predicted the formation of the hurricane's eye,
Right.
which is a feature you usually only see with those traditional physics-based models.
Wow. So it's got some serious potential.
It does, but as we said, there are limitations.
Right, like the speed issue.
Yes, and the researchers also noted that it has difficulty predicting certain variables,
Okay.
especially ones related to surface conditions like surface temperature.
Why is that?
Well, it's likely due to a couple of factors.
Right.
One, there just aren't as many relevant observations available at the surface compared to higher ups,
Right.
and the measurements themselves are more complex.
So it does better where there's more data and things are more straightforward.
Exactly.
But I remember you mentioning some ideas for improving these models.
Yes.
What are some of the most promising areas for development?
Well, one key area is refining that weighting system we talked about.
Oh.
By tweaking how different observations are prioritized, they can enhance its accuracy.
So it's like fine-tuning the settings.
Exactly.
Yeah.
Another avenue is incorporating an even wider range of data sources.
Okay.
Currently, it's mainly satellite data and conventional measurements.
Right.
But there's a whole universe of untapped data out there.
Oh, yeah. Like what?
Things like citizen science initiatives, privately owned weather networks.
That's true. We're collecting data all the time now.
Imagine if we could tap into all of that.
It would be amazing.
As these AI DOP models get more sophisticated, they'll be able to integrate all those different data streams.
So we're kind of giving them a sixth sense.
Yeah, a new way of perceiving the atmosphere.
With all this potential, what does it mean for the future of weather forecasting?
That's a great question, and that's what we'll explore next.
Okay. I'm excited to hear more.
There are so many possibilities from these hybrid forecasting systems to, the broader implications for how we understand climate change. It's a huge topic.
So we've been talking about the future of weather forecasting and all this incredible potential, but is it all about looking ahead? Or can these AI DOP models help us understand the past too?
That's a really interesting question, and you're right. It's not just about predicting what's coming.
Yeah.
These models can actually help us shed light on past weather events, too.
Oh, wow. How so?
Well, by analyzing historical data in new ways, we can uncover hidden patterns and connections that might have been missed before.
So it's like using these models as a time machine, almost, to unravel those mysteries of past weather events.
Exactly. It's like having a new lens to look back through.
That's fascinating.
For instance, imagine using these models to investigate, the factors that led to a major hurricane decades ago.
Oh, wow. Yeah.
We could potentially gain new insights that could help us understand those events better and even predict similar events in the future.
That's incredible. So it's like learning from the past to prepare for the future.
Exactly. It's about making those connections.
It seems like these AI DOP models are really giving us a whole new perspective on weather, both past and future.
They really are.
But you mentioned something earlier about hybrid systems,
Yes.
combining AI and physics-based approaches.
Right.
Can you elaborate on what that might actually look like?
Sure. So imagine a system that starts with those fundamental laws of physics, as its foundation.
Okay.
But then it incorporates the learning and predictive power of AI.
So it's like the best of both worlds.
It is. It's like having a master chef
Okay.
collaborate with a cutting-edge culinary AI.
Well, I like that analogy.
So the physics-based model, provides the basic recipe, the framework for understanding the atmosphere.
Right.
And then the AI comes in and it adds that nuanced understanding of how all the ingredients interact.
So it's taking that basic knowledge and then adding a layer of intelligence on top of it.
Exactly. And that kind of collaboration could lead to breakthroughs in weather and climate forecasting beyond anything we can even imagine today.
That's incredibly exciting to think about. But before we wrap up, I want to bring it back to our listeners.
Sure.
We've talked about all this potential to revolutionize forecasting.
Yeah.
But how could this technology actually impact our everyday lives?
Well, that's the key question, isn't it?
Yeah.
Imagine a world where you have access to hyper-local, real-time weather information
Correct.
that's tailored specifically to your needs and locations.
So like personalized weather forecasts.
Yeah, think personalized alerts about approaching storms.
Wow.
Optimized routes for your commute, even advice on the best time to plant your garden based on predicted rainfall.
It's like having a personal weather assistant.
Exactly.
That's amazing.
And the benefits go way beyond individuals.
Oh, yeah. Like what?
Think about businesses, governments, entire industries. More accurate forecasts could optimize agricultural yields, make energy production more efficient, enhance disaster preparedness.
So we're not just reacting to the weather anymore. We're anticipating it, planning for it, even using it to our advantage.
Exactly. It's about being proactive.
I love that. And AI DOP models like GraphDOP are making that possible.
They're paving the way.
Well, I'm definitely feeling optimistic after this deep dive.
Me too.
It's inspiring to see how human ingenuity, keeps pushing the boundaries of what's possible, even when we're faced with these really complex challenges like understanding and predicting the weather.
I couldn't agree more. And I believe that by embracing these new technologies, and always using them responsibly, we can create a future that's not just smarter, but more sustainable and resilient as well.
Well said. We encourage you to delve deeper into the world of GraphDOP and explore this fascinating world of AI-driven weather forecasting. The research paper, GraphDOP, Towards skillful data-driven medium-range weather forecasts learnt and initialized directly from observations, is available online if you'd like to learn more. Thanks for joining us on this deep dive, and until next time, keep looking up and stay curious.